Hello. Well, we are far from the well. We could be in front of an exploratory well, an appraisal well, infield well, whatever well we have. This holds, so we know the actions to make the highest potential in the well from the reservoir, and also we know the lifting system that is going to bring and the completion that is going to bring that potential to the surface according to an exploitation system. And we talked about the different lifting methods and how they apply in different conditions, right? Now we're going to see how we do this in the software. I have said before that since I have worked more with PipeSim from Schlumberger, I'm going to use some cases on graph that I have from previous studies, okay? So let's do some methods. Some hints also, even if we expect the well to produce naturally, we should estimate when it will die, and so we should include in the plan, we should install it, right? Also, if the rate that the well produces naturally is not enough for the economics, we have to install a lifting system, okay? In this particular case, PipeSim from Schlumberger, they allowed to design 3 different lifting systems: gas lift, ESP, and beam pumping, sucker rod pumping. So, what do we know? We have everything. We know the well it doesn't flow, or the rate is not very low, or the well is about to die. It's about to die. So we need a lifting system. And we have the red IPR, we have the transportation curve, and we know that we need to do a lifting system. That's why we're doing it in the software, because when we are going to talk to the suppliers about the details about the design of the system, we need to know details about how it works, and also about this. We need to know everything, okay? Everything, we have to know it. So, if we're going to do a gas lift well, which for me, if it applies, try to do it in gas lift. It's the best system. So, if we're going to do it from the scratch, this is a field that we don't know much or not very many wells, and we're deciding which system to install, the first thing we need to know is the pressure, the compressor pressure, because sometimes I know I have been in fields and in countries where the compressor pressure is high enough so that it's higher than the reservoir pressure. So we will not need discharge valve and mandrels, and that's a very good advantage. You don't need engineers, you don't need very many engineers to do the analysis, because you don't have valve. So if you're going to decide on the compressor pressure, try to get it higher than your reservoir pressure. If it is not possible, try to get it as high as possible, because we don't want very many mandrels in the well, okay? That's the case, that we don't need it. So, when we are going to design a gas lift well, like I said, we put the pressure we have available to do the design. In the gas pressure, we also need to know at what pressure the well is going to be unloaded, So we need to know that. We set a volume of gas that we can optimize it later, but we set something, and we specify the design of the spacing of the mandrels, like the pressure drop between each one of the mandrels, what the less depth we want from one mandrel to the other, and things like that. So those are safety factors about the design. And when we are ready, we click on perform, do the design. And that's what we get as an output. We get the depth of the mandrels, and we get the calibration of the valve, right? So we make sure that when we unload the well, we are going to be injecting gas in the deepest point, very close to the formation, because we want to produce the highest rate possible. Okay? That's gas lift. Don't forget, the gas pressure is very important. And ESP, which is also permitted in pipe sim, we remember the suppliers know very much about the pump, but we know about the pump and we know about the well. And normally the companies, they have contracts with suppliers, and we know the IPR, the site rates, we have everything, we know the GOR, we have everything, and we know that the optimum lifting system comes from a huge study. We have to study very much to decide, because once we buy a compressor, or once we put an electric station there for the pumps, we don't want to do things before we analyze very good which method is the best one, and we do it with all the team. Okay, so since we are designing our pump for 9,000 barrels, if you remember, we want this curve to cross here in 9,000 barrels, which is the rate that the team decided. So we look for the name of the owner of the contract, which in this case we decided that is Schlumberger, Reda, and we pick a pump that has the range where the rate that I'm going to lift is in between. So, and we set the velocity, the speed of the pump around 60 or 55 hertz, so that we can have, like here, we can have where to move in case we want to produce less or we want to produce more, according to the results of the water cut, whatever we decide, and we want a pump with that range, right? So, because we don't want to be out of this range, because the run life of the pump is going to be shortened, because the axe, the stage of the pump, they move across the axe. If they hit the thrust, the down thrust, they hit the axle very much, they're going to wear out. Or if they are too high, they wear up. So we want to be in this range. Okay? That's why we designed the pump in between. Alright, so that's something that we do in the software, and we do it like this. So we already know how to do a gas lift, we already know how to do an ESP. In the case of, by the way, this is what we are going to produce, around 9,000 barrels. And 9,000 barrels is around here. We're going to be here. We're okay. We can go low, we can go a little bit high, and we still have 65 hertz, so we can go up. Okay. So, the range is very important in the decision of the size of the pump. Anyway, we meet with the supplier, and we take care of the gas, we take care of the solids. If we're going to have, if we have threats of producing some solids, we should take care of the material, of the pump, of the motors and everything. Right? So, we are okay. And suppliers know how to do it. In the case of sucker rod pumping or beam pumping, the places I have worked, they don't have this option. They didn't have this option in pipe sim, so I couldn't use it. I used the key rod by echometer, so it's like I said in the last video, it's not hard to design. So if sucker rod if the well in the conditions states that I should use sucker rod, so we unload, we put the PI, or the bottom half flowing pressure that I assume I'm going to have. We estimate the diameter of the tubing. We set the strokes per minute around 6 or 5, and then we calculate and we see the rate. If the rate is according to the design, the rate that we decided in the team, we are okay. And then we can see the factors here in on the string, and also we also see the design of the diameter of the rods. So we put everything in there, and we even get the dynograph card. So we're set. So it's no hard. It's very easy to design. We have to be sure we have the condition clear, right? When we are in a steam injection project, we normally design for the well when the reservoir is in hot temperature conditions, and then after the reservoir gets the temperature lowers, we can change the unit. Okay, so that's the way we use sucker rod pumping or beam pumping. We use, like I said, in the cases of gas lift ESP, we use pipe seam, and also they have the option to design sucker rod pumping, but I haven't done it. Thank you very much. We'll see you next video. Thank you for being there. Bye.